Welcome to Physics with Joe. Let me start today's lesson with three simple questions. Question number one, can these two that was easy buttons exist at the same place at different times? The answer is yes. I have an easy button here, same place, different times.
That was easy.
Question number two, can these two that was easy buttons exist at different places at the same time? And the answer is yes, of course they can. Different places, same time.
That was easy.
Final question. Can these two that was easy buttons exist at the same place at the same time? And the answer is no. Physical objects, particles, cannot exist at the same place at the same time. However, waves can. And when two waves exist at the same place simultaneously, those two waves add together. And they can produce either a bigger wave, which we call constructive interference, or a smaller wave, which we call destructive interference. Today, I'm going to focus on interference because of a path length difference. Because one wave can travel a different distance than the other wave. And in essence, because of that, two waves can arrive at a point, at a phase, even if they start off in phase. So without further ado, let's jump right into it. In today's video, I'm going to focus specifically on wave interference because of a difference in path length. Because waves coming from two different sources can travel different distances in reaching a point. I'm going to assume that you're already familiar with the basics of waves and wave interference, and that you understand concepts such as amplitude, wavelength, phase, and so on. As a reminder, wave interference is governed by a very simple principle called the principle of superposition. It says the following: when two waves exist at the same place at the same time, the resultant displacement of the medium is the sum of the individual displacements from each wave. In essence, the waves add together mathematically at every point. From the principle of superposition, what we can see is that if two waves existing at the same point at the same time are in phase, which means both waves are at the same point in their cycle. So when one wave is at a maximum, so is the other one. When one wave is at a minimum, so is the second one. Then mathematically, when we add those two waves together, the end result is going to be a bigger wave. And if the waves are identical, so they have the same wavelength and the same amplitude, the sum of those two waves is going to be a wave with twice the amplitude of either wave. We call that fully constructive interference. On the other hand, if the two waves existing at the same point at the same time are at a phase, which in essence means they're opposite of each other. So when one wave's at a maximum, the second wave is at a minimum, and so on, then when they add together at every point, they cancel each other out. What you end up with is a wave with an amplitude of 0. Complete cancellation. We call that fully destructive interference. Well, let's take a look at a quick example to clarify this point. What this animation is showing are two different waves, wave 1 and wave 2, that we assume exist at the same place at the same time. And below that is the sum of those two waves. Remember, the sum is just governed by the principle of superposition. That just says mathematically I add the displacements of each wave together to get my resultant displacement. So if I want to know what is the resultant of two waves in the same place at the same time, I take the displacement from the red wave, displacement from the blue wave, add those two together, and that gives me the displacement of my resultant wave. In this particular case, the two waves are exactly in phase. Again, what that means is when the red wave is at a maximum, so is the blue wave. When the red wave is at a minimum, so is the blue wave. And when I add those two together, the end result is I get a wave that has twice the amplitude of either wave. We call that fully constructive interference. On the other hand, if the two waves are exactly out of phase, again, what that means is that when the red wave is at a maximum, the blue wave is at a minimum. When the red wave is at a minimum, the blue wave is at a maximum. When I add these two together, the end result is complete cancellation. I end up with a resultant wave that has an amplitude of 0. And we call that fully destructive interference. A quick word about notation. So here's another example where I've got two different waves, one in red and one in green, that we assume again exist at the same place at the same time, and the red shows the sum of those two waves. Now, when the sum of those two waves is a wave that has a bigger amplitude than either wave, we call that constructive interference. So here you can see the red wave, the resultant of those two, has a bigger amplitude than either wave. Now, when we're talking about fully constructive interference, that's when the waves are exactly in phase and the sum of those two waves has an amplitude that's twice the amplitude of either wave. It's really the maximum constructive interference you can have. Now, if we add the two waves together and they produce a smaller wave, so here you can see the red wave has a smaller amplitude than either wave, that is called destructive interference. And we usually reserve fully destructive interference for when the waves are exactly out of phase. When I add the two together, I get complete cancellation at every point. The resultant wave has an amplitude of 0, and we call that fully destructive interference. So let's finally take a look at interference because of a path length difference. And let me start by clearly defining what I mean by path length difference. So the figure shows two speakers, speaker 1 and speaker 2, producing identical sound waves, and those two waves can travel different distances in reaching an external point. Let's just call it point P. R1 is the distance from one source, in this case the top speaker, to point P. R2 is the distance from the second source, in this case the bottom speaker, to point P. Path length difference is really how much farther waves from one source have to travel compared to waves to the second source. We call path length difference delta R, and it equals the absolute value of R1 minus R2. In this case, waves from the bottom speaker have to travel a bigger distance, so my path length difference would be R2 minus R1. But we usually just use the absolute value of R1 minus R2. So let's say R1, waves from the top speaker had to travel 4 meters in reaching point P. Waves from the bottom speaker had to travel 5 meters in reaching point P. My path length difference would just be the absolute value of 4 meters minus 5 meters, or 1 meter. And what we're going to see is, depending upon what that path length difference is compared to the wavelength, the end result can either be constructive interference or destructive interference. Or more specifically, we're going to look at fully constructive interference versus fully destructive interference. So let's take a look at some examples. What this animation is showing are two different sources of waves. It could be water waves, it could be sound waves, it could be light waves, it doesn't matter. And those two sources are exactly in phase, which means that they are leaving each source peaking at the same time, reaching a minimum at the same time, and we're going to assume that this doesn't change, which means the two sources are coherent. Now, even though they start off in phase, again, they can arrive at a point in phase or out of phase depending upon how much farther one wave has to travel than the other, depending upon the path length difference. So let's first look at fully constructive interference, and let's start with the simplest case. If both waves travel the exact same distance in reaching a point, then if they start off exactly in phase, they are going to arrive at that point, call it point P again, exactly in phase again. So R1 equals R2, the path length difference is 0, and the end result is both waves arrive exactly in phase. We get fully constructive interference. Now, keeping in mind that a wave will repeat itself every wavelength, then if one wave travels one wavelength farther than the other wave, they are still going to arrive exactly in phase. So if let's say in this case, the bottom wave is traveling one wavelength farther than the top wave and reaching this point here, they are still exactly in phase. And if I freeze this, what's shown in red is the path length difference, how much farther the bottom wave is traveling than the top wave. Remember that a wavelength is the distance from peak to peak or from trough to trough. So here you can see the bottom wave is traveling exactly one wavelength farther. The end result is they start off exactly in phase and they arrive at this point here still exactly in phase, producing fully constructive interference. And it does not matter which wave travels the bigger distance. So on the other hand, if the top wave travels one full wavelength farther than the bottom wave, again, we still get fully constructive interference. And this will apply anytime the path length difference is an integer number of wavelengths. So if the bottom wave travels, the top wave travels 2 wavelengths farther, again, they start off exactly in phase. They're going to arrive at this point exactly in phase again. And you can see that the difference in path length is 2 wavelengths. So the condition for fully constructive interference for 2 identical waves that start off in phase is if the path length difference delta R is 0, or 1 wavelength, or 2 wavelengths, or 3 wavelengths, and so on. So when are we going to end up with fully destructive interference? Well, in essence, when the peak from one wave matches the trough from another wave, or when one wave is at a maximum, the other one is at a minimum, then those 2 waves are exactly out of phase and will produce fully destructive interference. When is that going to happen? Well, if one of the waves travels a half a wavelength farther than the other, so the path length difference is a half a wavelength, here you can see that the waves start off exactly in phase, but they are arriving at this point P exactly out of phase because the bottom wave is traveling a half a wavelength farther than the top wave. Again, this is going to happen anytime one wave travels an odd integer number of half wavelengths farther than the other wave. So if instead of the path length difference being a half a wavelength, here now we have the bottom wave is traveling 1.5 wavelengths farther than the top wave. So here the path length difference is 3/2 of a wavelength. And can I get 7/2 or 5/2? So now the bottom wave is traveling 5/2 of a wavelength farther. So the condition for destructive interference is if delta R, the path length difference, equals a half a wavelength, or 3/2 of a wavelength, or 5/2 of a wavelength, and so on, then the waves are going to arrive at a point P exactly out of phase and produce fully destructive interference. So in summary, for 2 identical sources of waves that start off exactly in phase, if those 2 waves travel a difference in path length of 0, or 1 wavelength, or 2 wavelengths, or 3 wavelengths, and so on, the end result will be fully constructive interference. On the other hand, if the path length difference is a half a wavelength, or 3/2, or 5/2, or 7/2 of a wavelength, and so on, we're going to end up with fully destructive interference. The way we usually write that is if delta R equals m lambda, where m equals 0, 1, 2, 3, and so on, then we have fully constructive interference. If delta R equals m plus a half lambda, where again m equals 0, 1, 2, 3, and so on, we get fully destructive interference. Now these apply if the waves start off from each source exactly in phase. Just sort of as an aside, if the 2 waves start off exactly out of phase, then this is reversed. So if the waves from the 2 sources start off exactly out of phase, then delta R equals m lambda is the condition for fully destructive interference, and delta R equals m plus a half lambda is the condition for fully constructive interference. Well, that is it for interference because of a path length difference. Thank you so much for joining me. I hope to see you next time.